Morning, everybody.
Good morning.
Just getting set up. Sorry, I'm a couple minutes late. I just was trying to reduce the number of slides in my lecture today. There's a lot of stuff I want to show you, but have to limit it to some extent. So I tried to, I didn't do very well. I was supposed to, this is how bad it was. I needed to get rid of 40 slides. I got rid of 20. I'm not going to show you all these slides. It's not going to happen. So what I'm going to do is it takes me a long time. I have to go through, like, read everything, look for redundancy, because like each slide has something a little bit different about it, but like not everything is critical. So I went through this process, but I ran out of time. So we are going to work with what we've got today. Anyway, so because I didn't delete all of them, I'm going to skip or go quickly over a couple, more than a couple, just to make sure that I have a chance to get to the end where I talk about groundwater. We start off with surface water and flooding, and then I talk about groundwater for a little bit. Are there any questions about the lab that I sent an email out 2 days ago, I think, that suggested you could use food instead of soil in your experiment. So food is always great for geology analogies or for just like real life experimentation. So I said that flour, sugar, cornmeal, mashed potato flakes, all of that could be used, or anything with a texture that's kind of granular, or yeah, basically granular, or could have like short grained rice might work, but that's probably more like rocks. That'll have a lot of pore space in it compared to the other materials. If you use flour, rice will be huge compared to flour. So I wouldn't mix sizes, but you could mix similar size food products so that they could act like different types of soils, like a sandy soil versus a clay soil that's gonna maybe, because it wets and because clay particles are sheet-like, they slip easily. And when you wet them, they slip even more easily. So some of those materials that I said, like flour, cornmeal, I don't know which of those might behave in a fundamentally different way. I think I might have read the mashed potato flakes is a weak layer. That seems to make sense because those will soak up water, kind of like clay does, actually. Some clay minerals soak up a lot of water and then expand a lot. That can help with landslides. So maybe the mashed potato flakes would swell up and kind of behave that way. Anyway, any questions?
Yeah, I actually have a question.
Okay.
So you said that we can use cardboard boxes, right? As like sort of our board.
Whatever.
Okay. And then for the soil part of the experiment, how do we like implement that on? Do we just like put that on first and then like start like how you say like rain on it, or like do we like put like?
Yeah. So I sent an email, right? And I explained a little bit in that email what to do. I suggested that you could use a colander with small holes in it, or a sifter, or even an open weave like cloth, like a cheesecloth might work, to pour a lot of water through those, and then it'll act more like rain that's spread out over an area instead of like just one area. You could use a spray bottle and mist it a lot until it's actually wet enough that it starts to flow or move. That would work. Use your imagination. You know, I'm leaving this up to you guys. So anything that you can imagine will work. You need to have a slope, right? So whatever surface you're working on, you need to tilt it, or the slope itself needs to be already tilted at least 30 degrees. If this is going to work. And if you start off with a too low of a tilt, you'll know because nothing will move. And then you can raise the tilt angle.
Mary, I have a question.
Yes.
For the last part of it, where we only choose one link,
Yeah.
we're only supposed to answer two of the
One event, not one link, but yeah.
Oh, yeah. We're only supposed to answer two of the questions down below, right?
That's right.
Okay.
So your choice, you choose the event that most interests you, or you can check them all out and decide which one you're going to work on. And then choose two of those questions.
Okay.
I'm just trying to reduce the amount of work that you need to do for this lab a little bit to make it easier on you guys.
Okay, thank you.
Mm-hmm. Any other questions about the lab? Okay. Well, what I'd like to do is, are you seeing my PowerPoint screen still?
No,
You aren't sharing.
yeah.
That's a good point. There we go. Okay. So I'll show you this. This was an impressive flood in 1993. They had a flood in Missouri. It's the Missouri, Illinois, Mississippi rivers that flooded, and that's St. Louis, Missouri here. And it was a huge disaster, and we're going to go into that a bit. I'm not going to read through these because you can read through them just to save time. Like I said, I'm going to skip over a few things that I might normally stop to talk about. But please interrupt me if you have a question, okay? Because as you've probably noticed, I get on a roll and I go fast, and I need to slow down for you guys, and it helps if you ask a question, frankly. But I get excited about this stuff and I start talking, and there you go. Okay, and I want to share this with you. Okay, so where's the fresh water? On Earth. We know that almost 98% of the water on Earth is saline, it's in the oceans. Then the other approximately, and then there's, wait a minute. Sorry, there's something wrong with that number. I'm confusing myself. Those numbers don't make sense, and I don't understand why right at the moment. It'll probably come to me. I will, and I can come back to this. For this, let's just put it this way: for the small amount of water that is on Earth's on land, the fresh water, there's a small amount of saline water on land, saline lakes and inland seas, that kind of thing. But most of the water on land is fresh water. The vast majority is tied up in the ice sheets, Antarctica, Greenland, and in glaciers that are up in the high mountains all over the world. The next largest reserve of fresh water is in groundwater. So that's about 14% compared to like 85% in the ice sheets and the glaciers. And then the everything else, like the lakes, the reservoirs, the water that's in the pore space of soils, water vapor in the atmosphere, rivers, that is, it makes up a very small percentage. So here, it's less than 1% total for all of that. the water cycle. We need to talk about how, like, kind of like the rock cycle, there's a water cycle. And there's so much to see in this diagram. I'm going to try to simplify it for you. I've been talking about, for several lectures, talking about how water, when it rains and water runs downhill, gravity is pulling it towards a base level, towards sea level, right? That's at least true for, regionally over a large area. Like locally, there could be a small lake that could be the base level, like up in the mountains, there could be a small lake where the drainage that's drains into the lake. But overall, that's part of regionally, the water is draining toward sea level. Okay. So the water's moving hill. It ends up in the ocean. The sea level is its goal, right? I'm not trying to anthropomorphize the water, but then we have evaporation. That's happening off of the land surface all the time. And certainly the evaporation is happening over the oceans. That creates clouds, the clouds move in, and there's precipitation, and the cycle starts over again. Now, some of that water actually seeps down into the groundwater. And so it's in the pore spaces of rocks that have pore space. So things like sandstone that aren't completely cemented. So there's still pathways for the water to move between grains. There's glacier and snow melt that comes off of the mountains and goes into the rivers that can temporarily end up in lakes, or that goes down the rivers all the way to the oceans. Let's see. Sublimation off of the snow and the glaciers. That means it goes from the solid phase directly to the gas phase or the vapor phase. It doesn't become liquid water ever. I think I've covered all of that. The groundwater itself can come out in artesian wells that is driven by gravity again. So that could be something like seepage here, where it's on a steep terrain and the water, I mean, this shows an incredibly steep gradient, and that's not realistic. But there could be springs. The groundwater could feed the rivers and keep the freshwater lakes at the level that they're at. And that's also pulled by gravity toward sea level. All right, I'm looking at it. I'm trying to decide if that's everything. 85, that's what I did. It should be 85-15. I'll figure that out later. This is obviously the correct number. 85% of the Earth's water is in the oceans, and 15% of it is on land. I don't know where the 98, I'm gonna have to figure out where that number came from. Okay.
Well, isn't
Never
that
mind.
referring to how much of the water is salt water?
Yeah, it probably is. Well, no, because that's sort of implied by this statement. Don't worry about it. I'll figure it out. I'll post it on the Q&A forum later, so if you're curious. Okay, so drainage basins and drainages overall. I talked about precipitation in the mountains moves downhill, right? Well, it does so in regions that are separated by high points in the landscape. So you might call it like the continental divide is one of those, where the high point in the middle along the Rocky Mountains in the middle of the United States, water basically falls to the west of the continental divide or to the east of the continental divide. But you can break up those those huge regions into smaller drainage basins that work together to get that water to the main river. So for example, like the Mississippi River has the Missouri and the Illinois River feeding into it. They're tributaries in a sense, they're large ones. This image shows small little streams that come down to a main river. And there's a ridge or some high point, a hill, something that separates this side of the hill from that side of the hill. Well, all of the water that falls within a certain, like this range of peaks or these ridges is going to go, I mean, it's headed towards this one river. Those rivers are going to join together at some point and meet larger rivers until the water reaches the main river, like the Mississippi. So I'll show you, wait, tell you what, I'll show you this. This is better. Okay, so this is this is the continental divide I was talking about. So right in the Rocky Mountains, we've got all of the water that to the west, and it goes, I mean, this is the whole, it goes up and down through Mexico, Canada, until Alaska. That's the large scale drainage basin, right? To the east, it all goes toward the Mississippi, not all of it, but a large amount. This dashed line is actually the drainage basin for the Mississippi River. So it's not everything to the east of the continental divide, but everything within that dashed line ends up in the Mississippi River, which turns out to be like the 12th largest river in terms of discharge. Anyway, so like I say, there are multiple, there are 5 different large drainage basins within North America. Okay. So in the up at the headwaters, that term sort of implies what it is, right? It suggests what it is. It's the place where the water begins, up at that ridge point, up at in the high peaks of the mountains. That's considered the headwaters. And the mouth of the river would be the end point, like where that drainage ends up, opens up to. The style of the river and the steepness of the gradient of the river changes depending on whether you're up in the headwaters versus whether you're down near the mouth of the river. If you just consider this diagram alone, you've got, this is called a dendritic river pattern, or just dendritic pattern. It looks kind of like moss or a tree branching. You imagine this big branch there with little branches off to the side. So that style is much more like what you find in the mountains. So with a high gradient, a steep slope, compared to down by the mouth of the river, where it's not nearly as steep, or maybe it's even flat lying. And in that case, you get what's called a meandering river. So it moves across the landscape and actually shifts within the sediments in the floodplain that we're going to talk about today. These streams up here could be cutting into the basement rock, the granite of the Sierra Nevada. And if it is cut down into the granite, then the stream channel is not going to move very much. But if the stream is moving through sediments, and if you've got a low gradient, this shallow profile, then you can see a lot of movement. And so that's what we're going to see differences of. I'm going to show you some examples. Originally, if you've got like uplift, just on a geologic time scale, if we've got uplift of a mountain and the ocean's off to the right somewhere, you're going to have this steep, you're going to have a steep slope separating the mountains from that lowland. Well, what happens is that the water itself, if it doesn't have enough sediment in it acts as an erosive agent and actually will erode the rock, erode the soil, and move it downhill. When the water when it's saturated in the sediment, when it has plenty of sediment, then you start to deposit material out of the water column. It just falls out of the water column. And so that's what this is representing. You're removing material uphill and depositing it downhill, and it smooths out that profile that you see for rivers. So you see like a smooth, oops, I keep doing that. You see a smooth curve instead of something that's like sharp and jagged with cliffs and things the water's going over. So this is the point at which a stream has reached an equilibrium point. But until then, there can be, you'll have a funky profile, but all streams sort of move towards the same curve. This is a lot to look at, but let me just break it down for you. There are 3 parts. This looks very much like the diagram I showed you 2 slides ago, with a dendritic pattern of streams in the rivers and a meandering pattern of the rivers in the low, like down by the mouth of the river. And I talked about how we have the sediment supply is up in near the headwaters. So you're getting erosion and taking that sediment, depositing it down in the low, I keep want to say the lowlands, but that it doesn't, I mean, I guess so, I guess that works. So there's plenty of sediment. In this case, it's showing you a braided stream. You can think of braided hair, I suppose. That's when you've got a large amount of sediment supply, you get that sort of stream profile. And in between, you have a zone that's where you transfer material. You're just moving it through the landscape. That's the first part of the diagram. This colorful diagram shows you the diameter of the material. So like your particles, sediment size. So from silt and clays up into sands, the very, very fine sands. And this is the speed of the speed of the river, the velocity of the water in centimeters per second. Okay, so if you have larger material, that's down on this right-hand side, larger material falls out of the water column. That's what this is saying, that you have to get really high stream velocities, stream speeds. Other words, the water has to be moving really fast to pick up large particles. Yeah. Then if it's small, if they're small particles, you're transporting those particles a lot. So that's what the blue field is, over a range of speeds from low to somewhat high. But if you get high enough water speed, then you're eroding the stream bed. So that's how to read this. Then the third part of the diagram shows, I don't want to use that label. Let's just use this, the distance downstream. So what I want to just point out is some important curves. So the dashed line that I'm following with my cursor is the stream discharge. That is the total volume of water that is moving down the stream at any given time past a certain point. And I'll show you how you figure that out. But it starts off low near the headlands and it increases as you move towards the mouth of the river. That makes sense because you're picking up water from the tributaries that are feeding down into the main river in a drainage basin, right? So all of this water is feeding down into it, and you start off with a small volume of water and it becomes a large volume of water. That makes sense, right? That curve. Then here's this dot dash, the Morse code curve, shows the relative volume of stored sediment, let's call it, instead of alluvium. You start off with a little bit of sediment and it increases as you move downstream. That makes sense too, right? So the larger the discharge, the more sediment that you're going to have carried in it. Then the profile of the stream is this smooth curve in the solid black line that I showed you in the other diagrams, that when a stream reaches equilibrium, they all have this smooth profile from headlands to mouth. The other curves you can not worry about. Those are for more specialist type stuff. But I just wanted to point to you how to read this. And this just conveys a lot of information in very little space. So that's why I wanted to show you that. You could probably work this out logically, just looking at a diagram like this, right? You could figure out there's less water here, more water there, less sediment here, more sediment there, steeper gradient here, lower gradient there. What else? Lower discharge here. I said that, higher discharge. I think I said all those things. Okay. So the variables that are changing to maintain this equilibrium once it's reached, so to get this smooth profile, are the discharge. So that's the volume of water the stream carries. Its load, which is the available sediment, so the material that's available to be moved by the stream, the gradient or the slope of the stream, and the channel pattern. I should have said that in the last diagram too. The channel pattern changes as well, but that you can't represent that on the plot, right? You represent that on this diagram. So the channel pattern, the sinuosity, how curvy the stream is, increases as you move toward the mouth of the river. So it starts off straight and it becomes curvier the closer you get to the mouth. So all of these things can be changing at any given moment to kind of maintain this equilibrium. Just quickly, how does sediment move? And this is like a whole course in itself in one slide, basically. This is your sedimentology and stratigraphy class right here. That's just a joke. Okay, so you've got a stream bed, let's call that just bedrock underneath, and you've got some sediment on the bedrock, and then you've got your water that's flowing across the bedrock. Well, you've got some large particles down here, the gravel size particles and sand size particles that are down close to the river bed. That's the base of the river, right? That's called the bed load. And those particles move by rolling, sliding, and this is called saltation, where they jump. You can just go jumping. So they move, yeah, they just jump. But of course, geologists have to create another jargon word for that. And the other sediment, the silt and the clay size particles, are part of the dissolved load, or the load that is suspended by the turbulence of the water. So this is the suspended load, okay? As you can imagine, and we've already talked about this and when we talked about sedimentary rocks, you're gonna find, if you were to look at a stream bed, if you were to take the water out and look at the stream bed, you could learn a lot about where you were on that profile of a stream, because you could look at the size of the particles. I guess you'd need to compare it one place to another on the same stream, but you get the idea. The coarser material is going to be found closer to the source or near the headwaters. The finer material is going to make its way toward the mouth of the river. And that's why you see these giant sediment plumes. If you've seen satellite images or just the like weather images on TV, that some of that at least gets moved out to the ocean when the river finally gets there. Okay. The discharge, I'm just going to summarize this. Don't try to write all this down. I'm going to give you the main points. The discharge, the total volume of water that moves past a point in a river at any given time, depends on the amount of rainfall and also the size of the drainage basin. Why does it depend on the size of the drainage basin? Because if you're looking at a large drainage basin, then you're getting more water filtering down into the main river. So you're going to have more discharge. And the more rainfall you have, the more discharge is going to be. It's reported as cubic feet per second, or CFS, or cubic meters per second, if you're going to go metric. A meter is about, it's about a yard, so it's about 3 feet. So this is significantly larger than a cubic foot per second. And you calculate the discharge, which is represented by the letter Q, as the velocity of the water, so the speed of the water in centimeters per second, or centimeters per second, or feet per second, depends on whether you're using English or and the cross-sectional area. So that's not just, I'll show you some diagrams, but it's, if you were to cut a slice across the river and just look at the area of water represented in that slice, that's what I'm talking about. So you would multiply the width of the river times its depth to get that area. I give you an example later on. The largest rivers are here. I got this off Wikipedia. It's good for some things, right? Most of the top 10 are shown in blue here. So a lot of them are in Asia, South America, and Africa, right? So the top river by discharge is the Amazon, which has some sizable tributaries. But just for reference, it has a drainage, a discharge of 209,000 cubic meters per second. That's huge compared to the Mississippi, which is North America kind of huge, which is, it's 14 on the list, which is only 16,800 cubic meters per second. So these are some big rivers, but the Amazon, just look how much bigger it is than all the rest. It's huge. And that's probably a result of the fact that this is on the equator. It's in the jungle. There's lots of rainfall. That helps a lot. And we're talking about a large drainage basin for the Amazon too. Okay. The Nile's not even on there, probably because it's in a desert, right? So not a lot of water as far as discharge, because this is a ranking by discharge. Locally, our top rivers are the Sacramento, American, Napa, and those are tiny compared to the Mississippi. Now, the Mississippi I've listed in cubic meters per second. So this is actually quite a bit larger than the Sacramento, right? Okay, stop me if you've got questions, please. You can put something in the chat because I can see the chat. Discharge changes seasonally, right? It's higher in the winter, lower in the summer. The more discharge you have, the more sediment it can carry. That seems logical. That's all that this slide says. Okay, the discharge. So here's how you work it out. And it's not so simple, right? Because this is not exactly, this is a curve. This is a weird shape. And to calculate the area of this, you kind of need calculus. Anyway, that's not necessary. We can just estimate, right? It's good enough for our purposes. And if it's a wide enough and shallow enough river, it's close enough approximation that we'll get our estimate, assuming a box will be like, assuming the same depth all the way across and one width. It'll get awfully close to the true area. This is the cross-sectional area that I'm talking about. So this is the slice. Okay, so that represents A. The velocity, you're told the velocity, you are not told the velocity. Never mind, I picked numbers. So the velocity is that measurement in cubic feet per second or cubic meters, sorry, feet per second. Yeah, it's feet per second or meters per second. That's what we're talking about for the area. The velocity. Jesus Christ. Sorry. Let me try that again. The velocity is just like in your car. It's miles per hour. It's a unit. It's a distance per a time unit, right? So velocity is meters per second or feet per second. The area is going to be 100 square feet. So square footage, that sounds familiar. Like if you're thinking about like square footage in your house, that's what we're talking about, an area. So the size of your kitchen at home, that floor area, the width by its length, that's how you calculate it. Same way. And like I'm saying, if it's wide enough and shallow enough, then that's a close approximation. But otherwise, yeah, there's a tricky curve. Okay, let's just forget about the curve. So let's just say a river is 20 feet across, and I'm just making this up, and it's 5 feet deep. So that's going to have a cross-sectional area of 20 times 5, which is 100 square feet, which is, 20 feet times 5 feet. I should always put your units in. Don't be sloppy like I just was. You got to use your units because you will catch your mistakes. That's why. So just do it. Trust me. Let's assume the water's moving 5 feet per second. And I'm just using English units because that's how hydrologists talk about it in this country. So if you've got 100 square foot area and it's moving 5 feet per second, then the discharge, or Q, is 100 square feet times 5 feet per second, which is 500 cubic feet per second. That's how you would calculate it. Okay. We're gonna move through some. These are all related, but it might be a little bit coarse since I haven't I've taken out some explanatory slides with a lot of text. I wanted to show you the diagrams and the pictures more so than a bunch of text slides. So bear with me here. Okay, so here is an active river channel, right? That's supposed to be water. And these are representing natural levees. So every time it floods, this river, like in the winter, it floods, it's going to fill up this area on the side. This is called the floodplain, right? And it's going to deposit sediment because with high discharge, you're carrying more sediment. And when the flood dissipates, when the water goes back down, it's going to leave sediment behind. It's mud, right? It's going to leave certainly silt and clay sized particles. If it was a big flood, it might leave sand or even cobbles or boulders behind. Okay. And when that happens, you get a natural little levee or a little ridge that's on the side, that's on the banks of the river. Okay, so that's a natural process. And when you go to just a natural stream, there's usually, you would climb down into the riverbed. That's what you're climbing down, is a levee. Now, if you've got active tectonics, like around here, you might see uplift of an area. Or if you're like back in geologic time in the Sierra Nevada, we're still uplifting. You might see multiple terraces. So there could be terraces up at a higher level that represent an ancient floodplain, okay? Okay, so depending on where you are in the river's profile, if you are high up, like near the headlands, right? And the river is cutting down through rock and it's a steep profile, that's when you get more erosion too. It's going to be cutting down toward sea level rapidly. And so eroding and carving a channel, there's the words I was looking for. It's going to be pretty straight because of that. It's going to be stuck in the, in its channel in a sense. Now, down low near the mouth of the river, you're going to have a shallow gradient. There's going to be, because the landscape is flatter, the river itself can move within a broader channel. And over time, rivers do move because with every flood, with every like high discharge period, you're going to get breaches of the levees. The river's going to break through the levee and it might form a new channel, right? Or you get a giant boulders blocking a channel and the river moves around it. It has that ability because it's in this flat area. It's in a wide floodplain zone. So the river can move back and forth across this floodplain. That's where people run into trouble. Is it's nice to live on a river, right? And certainly if you're a farmer, living on a floodplain meant that you had nice fertile soil that was replenished every time there was a flood. There was new sediment coming in. Problem is when you build on a houses near rivers or roads near rivers or anything on a floodplain, it can flood, believe it or not. And so that's problematic. Okay, what did I want to show you here? I don't remember, so we're going to skip over it. Okay, so I'm going to explain a little bit about this movement of a river across a floodplain. Okay, so here's an example meandering river. One reason that you're going to see shifts in a river's path over time is because at any given point, the water that's moving down this river, it's got slow places, like slower places where the water's places where the water is moving slower and places where the water is moving faster. The water moves fastest and the water is deepest, or the channel is deepest, on the outside of these bends. So here, like out here, and where on the insides of those same curves, you get deposition, or that's the slow point of the river. So you get deposition of sediment on these, what are called point bars, and you get erosion of the outside of the bends in these meanders. So you're eroding this outside channel and depositing sediment on this side. So gradually this river is going to move further and further this direction. Here's an example of the river having had done that. It moved, it eroded, and it moved out this way. But the river changed course and enough sediment piled in or was deposited here in these transitional zones, these riffles, that it closed off at some point, and the river just decided to bypass that area because of the sediment. And you're stuck with what's called an oxbow lake. It's an abandoned meander, essentially. Okay, hopefully that makes sense. There's a lot of text on this that explains just what I said, okay? So it's important to remember the deepest parts are on the outsides of these curves and the fastest water on the outsides of the curves. The shallowest places in the stream bed are on the inside of the curves, and that's where you get this deposition on a point bar. All right, so, oops. Okay, so there's just a typical meandering river active channel in a floodplain. During flood conditions, when it breaches its natural levees, then you can fill up that entire floodplain. That's what it is meant by it being a floodplain. You can see that really nicely in these false color satellite images, and so I wanted to share those with you. These are some meandering rivers, and you see the active channel in the dark blue or dark purple, and you see the oxbow lakes out here. And the floodplain is really visible because you can see that there's a shallow area around here where the river used to go, the course the river used to go, and it's changed course with time. So it becomes straighter and then it gets curvier and becomes straighter again and gets curvier. And so over time, that active channel is gonna move within the floodplain. That is expected, and that's the natural course of things. Depending on the discharge, so how much the volume of water coming down the river, you might have something that's considered the 10-year floodplain that would fill in a 10-year flood, or one that you expect to happen about once every 10 years. That doesn't mean it happens on the calendar once every January 3rd in 10 years. In 2020 and 2030 and 2040, we have a flood. That's not how it works. It's an average over a much larger time. So a 10-year flood is smaller than a 100-year flood, right? That sounds reasonable. The 100-year flood is 1 in 100 years. It means you have a 1% chance in any given year of having a 100-year flood. And that's a much higher discharge level and covers it fills up that riverbed, or fills up that channel to a much higher level than a 10-year flood would. So you can have such things as a 10-year floodplain. And so this is how they zone regions around major rivers. You might not be able to build on the 10-year floodplain, but the 100-year floodplain is okay. Like, that's the law. And so when you go to build a new house or make change, or add something, you've got to stay only on the 100-year floodplain, and you can't get closer to the river to be on the 10-year flood. That makes sense, except when you live through the 100-year flood. Maybe not even once, maybe it's twice in your lifetime. So that can happen. I'll explain some more in a second. So levees, natural levees. Here's just a normal, well, it says flood stage water level. This is before the flood. Oh, this is the flood stage. Yeah. This is before the flood, obviously. The water is in the channel completely. Here's the flood stage water. So the water has filled up the channel and it has spilled out over the edges, and it's filling the floodplain, right? And it's also depositing sediment as the water is moving out of the channel, because the fastest waters move is down deep in the channel in the center here. And it's spilling over the edges, and so it's carrying the sediment with it. So the heaviest material, or the largest particles, fall out first, and the clay and silt move farther out to the floodplain. That's why you end up with a levee. And over time, you build them up higher and higher. So it's possible to be living below, and this happens out in the Sacramento Delta. Like, people live in places up to like 25 feet below the river, the normal river stage of the Sacramento River. It's crazy. Actually have houses on stilts. No kidding. I was going to show you a video, but you can Google it if you want. Okay, so levees can be natural, and you can also build artificial levees that you would use, like pile sand up around a river to try to keep it in its banks. You're making the river channel deeper in that way too. But there can be problems with artificial levees. And I just want to point out a few things about that. This is probably not, this slide is not in the right position, but I'll just go ahead and explain what it means. Okay, so stick with me here. The dark gray, this is the natural stream bed, okay? And water might be flowing in a normal day down here at the bottom of the stream bed. And when it floods, maybe it floods out up to here or something like that. But you want to avoid that. So you build an artificial levee. That's this white thing here. Okay. And this white thing here with the specks. So you build levees to try to make that channel deeper so that you can build on it. Problem is that when that channel floods, it spreads over a much larger region than if you had just left the channel alone and allowed it to stay in its natural stream bed. So it can cause more damage to have artificial levees like this. And I'm going to get to, oops, I didn't mean to do that. I'm going to get to examples about how that works. This is in the wrong place too. This shows the stream, the speed of the water moving in the stream bed. So on the outside of the curves, it's deeper, and the fastest water is in the dark blue. In a wide open river, the fastest water is in the middle near the surface. I guess that's near the surface as well. Don't worry about the rest of it. I've explained all of that already. This name, the outside of the curve, is given the name cut bank. And it is what it sounds like. It cuts into the sediments on that side. It's erosive. Okay, and it's also the fastest water. So these are some cut banks and point bars on a river. So check it. There's a little like cliff here. I mean, it's just cut away into the sediment, right? And here's the point bar. So it's gradual, and that's where the slowest water is. And it's depositing gravel and other material here. And it's eroding the channel out here. Same thing here. It's moving fastest there, and then fastest there, fastest here, fastest there, like that. And here's some other examples in different terrains. If it's more gravelly, up higher in the mountains, you get the same idea. So point bar and a cut bank. Cut banks are erosive. Here's an example of that erosion. Here's a cut bank. Here's the same cut bank after a flood. I think you can see that it took away a lot of land, a lot of sediment at that point. This is probably, well, okay. I've already said near the headwaters, stream channels are straighter, and they start to migrate and enlarge their floodplain over time, or as you move down the stream profile. So toward the mouth of the river, okay? Just in general. Here's some nice examples of meandering rivers. Same idea. I'm not going to re-explain that diagram. Here's another beautiful meandering river with some oxbow lakes. I think I already showed you that one. Yeah, because I think I showed you this already. Thought I caught all those. This is the process, right, that you might go through in a natural stream to create an oxbow lake. These outer curves here are erosive. So over time, you narrow this neck in between the two outer curves. This is building out this way, it's eroding out this way. These are eroding until actually you cut through that neck and the stream bypasses that oxbow lake entirely. If you've ever been river rafting, you might have gone past one of these channels where there's a side channel that the water is moving much more slowly. Well, probably over time that's gonna be bypassed. So here's the oxbow lake in the end and the channel having cut through that neck. So here it's gonna eventually cut through. Here it's gonna cut through. Oh, there first probably. Or there, or there. This is really narrow in here, but you can see the places where that would happen. This has to migrate some more before you would get that action happening. Here, that one's too wide. Okay, I'm gonna skip this. So just to summarize kind of, I wish this was in the other direction. Just, this is close, more like upstream. Near the headwaters, you get more braided streams. That's because there's too much sediment for the amount of water or the amount of discharge in these rivers. So you end up with this braided pattern. Downstream, where there's higher discharge, So more water, you tend to get, well, you're also moving from a straighter stream path to something that's more sinuous, right? And closer to a meandering river. But given a flat enough area, then that river it's going to exaggerate the curves that develop until it becomes a meandering river. So what can you say about the differences between a braided river that's more like upstream and a meandering river that's downstream? Look down here to just get an idea. There is, well, this is separating the bed load from the suspended load. I was going to say there's less sediment here in the water, more sediment here. Up here in the headwaters, it's more bed load. So it's the larger pieces that are moving along the riverbed. Down here, it's more suspended load. It's the silt and the clay that is being transported by these rivers. So this is finer grain material, coarser grain material. This is an erosive area. So it's the banks of the river aren't stable. It's eroding. It's eroding actively. Down here, it's closer to its kind of final configuration, despite the fact that the meanders are moving over time. The discharge variability. Okay, so you can get storms that will change the discharge in these streams briefly and rapidly compared to down here. Downstream, it is more consistent over time because it's further from the source of the water. This is on a higher slope, a steeper slope, and this is on a lower slope. That's what I'd say to generalize. Here's a nice headwaters picture. Waterfall, because we're in the rock, the river's cutting down through the bedrock. So you've got waterfalls, you've got rapids, and it's steep. So this water is moving fast and it's eroding down in that channel. This is what a headwaters region would look like, right up here. So this channel, even though this is a flatter area in this meadow, the channel is going to be straighter than if you were closer to the mouth. You also get braided streams near the headwaters. So this is where you've got low discharge and a lot of sediment because the water is eroding the rock. So you get just many channels. I'm not going to worry about all the different terminology, right? The main point is there's like a main channel and you've got all these subsidiary channels. Some are abandoned and they're just like little ponds. And you're building up these what are called channel bars, the sandbars. Don't camp on a sandbar. just FYI, especially if you're up. Oh my God, I got stuck in the Himalayas once. It wasn't that big of a deal, but there was this tiny little trickle of a stream through our campsite, right? It was a nice flat, we were on a floodplain, but it was like for a big flood. But it was there was donkeys braying all over the place. We were in a little village. Anyway, I set up my tent on the other side of this little tiny stream. Well, guess what? We got there in the late afternoon and we were at 15,000 feet elevation. So it's fairly cold at night, even in the middle of the summer. And over the course of the days are beautiful. It'd be like 80 degrees out. I'd be in shorts if I could, although I'm respectful, so I wear pants when I'm in some other countries, depending on the culture, right? So it's nice and warm during the day. It warms up glaciers, the glacial ice too, over the course of the day. And you don't receive that water until later in the day. So it starts to melt and the trickles and the drips are all filtering down to the mainstream over the course of the day. So what happened was all of a sudden I heard one of the worker dudes say, "Pani, And I hope I'm saying that right. It means water. And I look over and here's this flood of water, like literally like plug of water just coming down all of a sudden. And it got bigger and bigger and big. And there was more and more water. And suddenly this trickle was like 8 feet across. Shit, I was stuck, right? My tent was over there and I was on this side. I ended up, I think it was one of our drivers or one of our cooks, and it was a fancy camp. We had the senior geologist with us, and so it was a fancy campsite. They brought an extra vehicle just for all that stuff. Anyway, jumped across this. He could jump farther than I could, and the guys held a rope for me, so I got to hold on to a rope to get across. I thought like, I can do this, I can jump across this, but I didn't want, it was cold and I didn't want to fall in and get wet, and then my boots would be wet and then they'd be wet the next day and the next day anyway. So I didn't. Don't camp on a channel bar for that very reason, because you don't know if there's going to be an afternoon thunderstorm that's going to send a flash flood down the river. And yeah, that could be you out there. So imagine, yeah, it was a much smaller scale, but imagine my tent out here and me on the side. It was, yeah, it was a problem. Okay, so this is a really big river. Here's the main channel, but clearly with more discharge and over time, this river has filled this entire floodplain. Okay. More beautiful I just wanted to show you beautiful pictures of meandering streams. You see the natural levees on the outsides there defined. You see the oxbow lakes and the very old meanders that are still scars in the landscape. You might get a dendritic pattern. This is going to happen on steeper terrain, so up in the mountains near the headwaters. Remember, this looks like dendritic means like a tree or like a moss type pattern. All these little tributaries filtering down to the mainstream. All these come down here. These are all of these little streams are tributaries to this one. This is a tributary to this mainstream. You get the idea, I think. If in certain terrains, like out in the desert, or like I'm thinking like the Colorado Plateau, where there's rock, it's exposed rock, and the rivers that flow there, at least in some cases, might follow fractures in the rock or the bedding pattern in the rock, jointing. You can see this pattern here in the bedrock. I don't know why this formed, but it's there, and the river is following all these fractures. It's like got this squarish pattern to it. So this is not unrealistic. It does happen. Okay, the mouth of the river, we're there finally. Oh, we are not getting to the end of this. I'm going to have to skip more slides. Okay, deltas. This is at the end of the river after it's flattened out and as it's emptying into the Gulf of California, the Gulf of Mexico, or the Mediterranean in the case of the Nile. You have a main channel, but this channel has moved over time. These are same idea with floods, with rivers breaching, natural levees are breached, and the river can change its course. And you can see those old paths here. It used to go out this way and then this way, and right now it's right here. This is the modern delta. You can see the suspended sediment load in these plumes out here, right? The plume of sediment that's out in the Gulf of Mexico. You can see it kind of out here in the Nile River Delta in the water there. This is from the space shuttle. Oh, isn't that dated now, right? Space shuttle image. And they have kind of a fan shape to them. This is similar to, oh, I skipped right over this. This is similar to what you get in like a desert environment, where you get alluvial fans. So these are sediment fans out like in a desert or arid regions. where you might have afternoon thunderstorms bringing flash floods down out of the mountains. It's eroding all of that rock. And then as soon as it hits the flat valley floor, this is Death Valley, when it hits the flat valley floor, the water speed slows down suddenly because it's not on a steep gradient anymore. The gradient changes, so the water speed decreases and spills the sediment load. I'm skipping. You can have regional floods, which cover, I didn't mean to do that. You can have regional floods. That means it covers a large area. For example, flooding the Mississippi River Valley. This blue, okay, so in the red line is the entire drainage basin for the Mississippi. That's 41% of the continental US. It's huge. In 1993, there was a flood that filled up this entire area in blue. It was huge. Here's some of those images, the before and afters. Oops, I moved my bar. Here's the before. It's in its channel, but you can see the floodplain, right? Like there's an old meander right there. Here's an old path. There's a cutoff channel there. So it could fill up this area. Luckily, it's mostly agricultural land. You can see the rectangles and not city. There's city, there's city. So they've kept the city away from the floodplain, but not entirely. Here it is in the flood stage in 1993. You can see a highway that cuts across here. The channel that used to be, and then the flooded area. So it's filled most of this area up to that old meander. So it's filled the entire floodplain. Here where it's straight, there are artificial levees. And here also, it's very channelized and it's very straight. Artificial levees have been built to try to protect the cities and residential areas. And that causes worse flooding in other areas. So if you protect this region, that might mean this area floods over a larger area. Here is the before picture of the Illinois, the Missouri, or I got that backwards. I think it's the Illinois, the Missouri, and the Mississippi. In 1993, this is what it looked like. So this is just like the main part of the flooding, but you know what you can't see is even this whole area is all flooded. It was a disaster. It looked kind of like this. So this is Iowa, this is Missouri. They tried to put up like these little silly looking barriers here to stop the water. I mean, it does kind of, it works right there, but it just crosses the river there and wipes it out. There's a sports stadium. So it was bad. This is the discharge in cubic feet per second. In a typical flood stage would be down here, 450,000 cubic feet per second. 1993, it reached this high, over 1 million cubic feet per second. So it was huge. And that lasted, it lasted like a month. Yeah, it was forever. Okay. Part of what causes floods to be bad are like really long periods of rain, so that the soil is saturated, meaning that when it rains even more, there's nowhere for the water to go because all the pore space in the soil is already occupied. So the water runs off the surface. There are meteorological conditions that can cause additional, like extra wet winters. La Niñas and El Niños cause extra wet winters in some locations. Ugh, whoops, skip it. Artificial levees. So you can see the artificial levee right here, how straight that is. And look at the floodplain. You can see the Oxbow Lakes and you can see the old meanders here. And they're trying to control it because people live here. This is in 1927, there was a huge a huge flood. See all the people on the levee? This is the levee. That was the highest point around. They were all living below the level of the river. And so they all went up and camped on the levee. This is, okay. There's a video that some videos that show, this is an experimental setup showing a natural river that's in flood stage where the banks are overtopping versus having levees come in and what happens when you have a flood. So when you increase the discharge here and the levees are breached, you flood this entire area. So nothing is protected. Whereas here in a natural setting, it's just overtopped its banks and it's soaking in to the soil around the river, and it doesn't cover nearly the same area as if you had tried to control it with the levees. If you put a levee on one side and not another, or if you put a higher levee on one side and not another, you're going to cause worse damage, worse flooding on the side with the lower levee or without the levee. In the cases where you get very high, big floods. Here's what a non-flood stage might look like, natural rivers. Here's what a natural flood might look like. And here is what a flood might look like with levees protecting certain areas. So like maybe you have a power plant that can't flood or else everyone's going to lose electricity and it's going to cause damage for a long time. You want to put a levee up around it or a nuclear reactor or something like that, right? You don't want it to be damaged. You put the levee up and what happens is it causes worse flooding elsewhere. So there's worse flooding. It's much deeper water where it's darker purple, much deeper and more expansive flooding up here compared to the natural stage when you've got this flood. So you're channelizing more water into this area. Instead of flooding down here, it floods out here. Okay, so there's a lesson. This graph, all this says is, this is the actual like discharge for a river over many, many years. So almost like 100 years. And it's showing you when it's flooded. Okay, here's the 10-year flood line, that black line. And the red bars that go up above that line are flood years. So 1, 2, 3, 7, 8, 9, 10 floods in about 100 years. That's what gives you the 10-year flood. That's how you determine it. But look, that the distance, the time period between each flood is not 10 years. Here's 17, here's 11, here's 5, here's 7, another 7, 4, 7, 28 years, 6 years and 6 years. So it's not like clockwork. It is an average. This is the same with like earthquake prediction, right? Or probabilities. Okay, a lot of information here. Look to the right now. So I'm talking about 100-year floods. The 10-year flood means that there will be 10 in 100 years, or that in any given year, you have a 10% chance of having a flood. A 100-year flood is once in 100 years. So it's an even larger flood in order to and it happens more rarely as a result. So it's a 1% chance in any year. The 1,000-year flood is even bigger flood, meaning higher discharge. It's 1 in 1,000 years, and you wouldn't want to be around for that. The point here is, and you guys don't own your own houses yet, I don't think, but your parents might, or your other family members might. A lot of people get a standard 30-year mortgage. You pay the bank and you pay off your house over the course of 30 years. So if you buy a house, and like this happened in Houston, Texas, not so long ago, residential neighborhoods were flooded. And I'm sure a lot of those people had 30-year mortgages. The chance that your house will flood at least once during that 30-year mortgage, as you're paying off your house before you even own it completely, is 1 in 4, is a 26% chance. That's pretty high. I mean, that's not everywhere, right? You need to be in a area like around a river, in a 100-year floodplain is where you need to be. So not too close to the river to be in the 10-year floodplain, but up higher, away from the banks. Okay. The chance that your house floods at least once in your lifetime is 55% chance. That's pretty high odds. And the chance that your home might flood twice in your lifetime is 14% chance, which seems awfully high for a 100-year flood twice in your lifetime. So I just wanted to bring these home, punny, to you, just to explain it that way. I'm skipping this and this, enough graphs, more pictures. Okay, flash floods are the other kind. So we had regional floods like the Mississippi, and flash floods are what we get often in desert regions where there's steep terrain, not very much vegetation, and so there's not a lot of soil either. So meaning there's not a lot of soil for the water to soak into. There's not a lot of vegetation whose roots would soak up some of the water, right? And because it's steep, you're probably dealing with more rocky terrain. Here's an example of in the Colorado Plateau. This is the slot canyons in Utah. This is amazing to get lost in, by the way. Look at how there's my buddies there. These slot canyons would easily fill up in a flash flood. So if you go in a place like this, it's a park, it seems safe, you're out in the middle of the day. If you hear thunder or see dark clouds, you better haul your behind out of the slot canyon, no matter how much fun you're having, because look at these boulders. The floor is down here. These are suspended 10, 15 feet up high. That means the water was at least 10, 15 feet high in the slot canyon and carrying rocks as big as these boulders. That's what that means. So that's not a place you want to be during a flood. And if you are in a place with a flood and a flash flood happens around you, climb to safety. Just get higher up. Don't try to cross any flood waters because you don't know how deep that water is, number one. Even if you think you do, you don't. And half of all the fatalities that happen in flash floods are related to people trying to cross in their cars. It only takes 2 feet of water to carry away most cars because they're kind of buoyant. And there's a lot of force that comes in in the flash flood water. Okay, just some lessons to learn. Here's some couple of trucks that got caught up in a flash flood. These might have been guys saying, I'm in a truck. I've got 4-wheel drive. No problem. I say guys because I would think only a guy would do this. I wouldn't. Yeah, don't do it. They got carried away. I'm assuming that maybe these were just parked somewhere in the area that got flooded, right? It doesn't mean someone was crossing the flood at the time, but it could be. One way to control floods is also with dams. Problem with dams is those can be breached too. Here's an earthen dam and a breach. We had something like this just happen in Oroville, up near Davis, like UC Davis area, not so long ago. I don't remember which year. It's probably 5 years ago now, at least more, maybe 7. So they don't always last, especially if you build up the water. If you're trying to store water in the dam so that you don't flood the land that's downhill from the dam, you can breach the dam too, and it just pours over the top. And once you do that, then you start to erode the dam, break it up, and then the dam is gone. Okay, so they do fail. Just, I don't know. I don't know that I've written this question, but here's the idea. This is an important concept. Once a place is a floodplain, it's always going to be a floodplain. Meaning when you get to a point in your life, you're choosing a place to live, maybe you're buying a house, probably not in California, right? With the cost of houses here. But maybe you move out to Houston and you buy a house. The last time that storm that I was talking about that took out those residential neighborhoods, there were people who had experienced, that was the second or even third time that their house had flooded, and they built right back in the same place, probably because they owned that land. And where else are they going to move to? They can't afford to move somewhere else. There needs to be legislation, laws made to say that once an area has been taken out, like you need to relocate outside that floodplain. That's the only smart thing to do. And that even comes up with like Hurricane Katrina and New Orleans. Like, would you want to relocate New Orleans? Because those places have a historical significance. And so that's tricky. That's tricky. That was storm surge and failed levees that caused that damage back that year, 2007, something like that. Maybe someone knows. Flood insurance, if you are on a floodplain, if you are silly enough to live on a floodplain, you probably ought to get the flood insurance, right? Because what happens when you don't, you're left to, you got to deal with FEMA, the Federal Emergency Management Agency, and they will not necessarily give you enough money to rebuild your home. So the only way, you're just going to be SOL if you don't have flood insurance. Urbanization. We're going to do it, you guys. We're going to get there. Okay, I'm going to get us through this lecture and get all the goodies. Okay. In urban environments, there's a lot of pavement. There's asphalt and concrete. There are huge parking lots for Costco and big box stores. There are freeways and driveways and sidewalks. All of those things, sewers, all of those things, buildings, concrete channels where for the streams where there used to be natural earthen stream beds. All of those things mean, like, when you pave over a natural area, when you pave over the ground, the soil, you're taking away nature's ability to deal with floods. Because when a river breaches its banks, the first line of defense is water soaking into the soil, and vegetation taking up that water. So you can create worse floods because of that pavement, is my point, I guess. Okay, so here, this graph describes what I'm talking about. So this is called a hydrograph. You don't need to know the name of it, but the dashed line, let's look at the dashed line first. This is stream discharge, so the volume of water, and this is time. Here's a rainfall event that happens right here at the beginning. Let's follow the dashed line. It's cool, no problem. But then finally the water filters down from the tributaries into your stream. And so you've got this big plug of water, a huge volume of water that is discharged downstream. This would be like in a natural area, a watershed where there's soil and vegetation, all of that, trees, to soak up the water. That's what the flood would look like. In an urban environment, so with buildings and roads and reduced amount of soil, reduced amount of forest and vegetation, what happens is that flood stage is higher. So you get a higher discharge down a stream because more water is reaching, there's less water that's being soaked up. And so there's like a higher level of discharge in the actual stream. And that means that, like overtopping the levees, you're going to flood a larger area than you otherwise would have. So this is the idea. Discharge time, same thing. You have a lag time in between the rainfall event and the peak discharge. That's what I should be calling it, peak discharge. If you install storm sewers, you have a shorter lag time and a higher discharge. With extensive urbanization, meaning lots of pavement, lots of big box store parking lots, you have a shorter lag time between the rainfall event and the flood stage, and discharge is even higher. So it just gets worse the more you change the natural environment. All right, we did surface water. Now onto groundwater. Okay, so that was all what's going on in streams and rivers and whatever you want to call them, right? On the surface, how pore space in the soil soaks up water. Let's talk about groundwater. And in this case, this could be rainwater that seeps through the soil and filters its way down into an aquifer. So an aquifer would be rock that has pore space in it, like let's say a sandstone that's not well cemented. So you've got sand grains, there's a little bit of cement in between the grains, this brown stuff, but the white space is open space. Water can filter down through that. And if this whole section is that sandstone that's permeable, meaning it's got that pore space and the water can permeate it. The water fills that pore space. And if you had more rain, it might fill it up to this level. Whatever level, the top point, the highest point of that water that's in the ground is your water table. Okay, so that's the top of that's the top of the water table. The whole hunk of rock that is permeable is an aquifer, meaning it can hold water, but the rock doesn't necessarily have to be fully saturated, is what I'm trying to say. Okay, so this is how it works. Streams that are there year round are there year round because the stream bed, the stream channel intersects the water table. So here, for example, the mountains, water is filtering down into this aquifer, and the top of the water table is here. There's a gradient, just like there's a slope on the hillside. There's a gradient with the water. And, it might intersect the surface and you get a spring here and there, right? But it's discharging in the stream bed. So the water kind of percolates along these arrows. So it's moving through those pore spaces to get to that stream bed where it emerges. This is what I mean. Okay, so here is, these are supposed to be like sand grains, kind of angular quartz grains and feldspar grains maybe. And the blue space is where the water can infiltrate. If you've got fairly uniform grain size, right? So it's homogeneous. If you have a heterogeneous grain size, so large and small grains, you're going to have less pore space. And of course, you can't have cement filling up all that pore space. So there has to be some actual open space between the grains for the water to fill. And there has to be connectivity. So this water has to be able to connect to this pore space water, has to be able to connect to that pore space water, has to be able to connect to that in order for this flow to happen. along these curves. Okay, not all rocks can be aquifers. And it kind of depends on the porosity of the sedimentary rock. If you've got, so down, it's porosity on the x-axis and different rock types on the y-axis, okay? So the highest porosity rock types are, these are silty or fine sands or coarse sands, so sandy material, even some clay material, but not completely because that doesn't work like that. In an area with weathered granite, that kind of behaves kind of like a sandstone. So those are the best. A limestone can also have lots of pore space because if you've got any sort of acidity to the water, you will have dissolution. You'll dissolve some of the limestone and create caves even, or at the very least pore space. And so those can be good aquifers. The ones that are down here, like this clay, which would make like a mudstone, I suppose, or shale, or just bedrock, solid rock, like a granite. They're impermeable, and those get another name, which is an aquiclude. So there's an aquifer where the water can permeate and fill up to a certain water table. So here's the water table in this case. It's up this high and it's here, intersects the stream bed here. So it keeps that stream running year round. This is the recharge area. So you're recharging the aquifer, meaning you're putting water back into the aquifer when it rains. I realize I've gone past 12, but I'll be done really soon. And this is the last class of the semester. So the last time you have to go past noon. Okay, those other rock types, like either maybe bedrock down here, solid bedrock, or a shale mudstone layer is going to be impermeable. And that means the water can't pass through it. So you might get water confined to a particular layer in the rock, or it might be unconfined or open to the land surface in some places, like for springs or rivers, for example, or lakes. So these are aquifers. These are aquicludes. They preclude flow of water. Okay, I don't have that many left, I don't think. Yeah, I don't have that many left. I will go quickly. This is the same idea, actually. I've already described this, so let's go past. San Francisco. Here are the groundwater basins of San Francisco. And I just wanted to show you an example of the West Side Basin here that goes through Lake Merced. But you see that there are other small basins that probably originally had these streams in them. Remember, we looked at those maps of all the areas that you would get liquefaction in an earthquake. Those are all those, the mouths of those streams that were originally there before they got paved over, right? Here is what it looks like. So this is the groundwater basin outlined in green. And this is the line, the blue line, AA prime, is this AA prime. Okay, so this is a cross section through the ground. This is kind of parallels Ocean Beach. There's Lake Merced's San Francisco States right there. That's why I chose this one. And what you see are, okay, so there's some, these are metamorphic rocks down below. So this is the bedrock that is impermeable. So it acts like an aquiclude. Then the area that's in blue are the aquifers. There are some layers, and we know this because there's been drilling. There are clay layers in here. And this layering probably has to do with the, over time, the buildup of streams, either at a high water stand when you're getting coarse sandy material versus clay material when there's low water, or when, yeah, just with changes over time. So you see Lake Merced there intersects the water table. So the water table is the dashed line there. Notice that there's a dip in the dashed line there. There's a well here, and they're tapping the aquifer from this well. And what you get a depression cone, a cone of depression, that means that if you tap the water out of if you take groundwater out of the aquifer faster than the rain or precipitation recharges that water into the aquifer. Everyone with me with that? So if you take water out of the pore spaces by pumping it out in a well, and faster than you can put it back in through rain, then you'll see the water table will be at a deeper level. So over time, you would have to drill deeper and deeper wells to get at that water. That can have an effect on your neighbors, and so some property disputes can come out of that. You know what, we've already, oh yeah, okay. Shoot, I hope you didn't see that one. Which location would be best for drilling a water supply well? Here's a question. Consider the water quality as well as the quantity. And it's showing you a water table here. You've got impermeable rock in gray, clay layers, and permeable rock in green. So all these wells, well A goes to this confined aquifer down here. Well B stops in this impermeable rock, and well C stops in this unconfined aquifer here. Which one would be the best well to drill, and why do you think? Does anyone have any thoughts? We'll be done by quarter after, I promise. Oops. Does anyone have any thoughts? It's okay. If you're not brave to guess, I'll just give you another second. Brave people? A. Why though? Can someone type in why? More water? Oh, okay. You think there's more water? All right. That could be true. What else? Let's say this is urban San Francisco. What else could affect more permeable rock? Okay, it's deeper. Okay, notice that this is confined, meaning it's between these two aquicludes. So this water is kind of physically separate from this water. Better water quality in A. Why is it better water quality in A? I know these are kind of hard questions. Okay, when it rains, right, it fills up, it's going to recharge the aquifer and fill the water up into this space up here, but not here, at least not directly. It might over to the left or to the right, up in the mountains maybe. But how? Okay, I'm just going to give up.
Doesn't impermeable rock mean like it's like hard to penetrate? So,
yeah, okay, there's no water in this one. Yeah, B is just you're out of luck if you stop your well there. There won't be any water. But what about
like, A
is better? But C is good too, right? It ends in the aquifer. Why not C?
Well, because
okay, great. Go ahead, Michael.
Sorry, A because A was able to dig through two layers of impermeable rock.
Okay. Yeah, the fact that it's separate is good because Davino gives us a great explanation. There's a higher chance of contamination on the shallow aquifer, and there's less impermeable rock. Okay, I'm not sure what that last part means exactly, but I think you're totally right that this aquifer is physically separate from this one. Pollutants can also sink down into the aquifer, into the groundwater, and mix with the groundwater. So leaky gas tanks at a gas station, a business that, let's say a paint business that isn't disposing of their waste properly and they're dumping it out back in a big disgusting pond. A tanker truck spill on a highway. All of those are ways that you can get gasoline, other chemicals into an aquifer, and that you would have a contaminated aquifer. If you were near the coast, you might even get saltwater contamination, because if you pull enough water out of your aquifer, you can actually pull the seawater in. That's for another day, but yeah, A is the best choice, mostly because it's less susceptible to contamination. Okay, cool. Thank you for volunteering, everybody. This is the same, this aquifer aquaclude idea, I'm just going to mention this quickly, works for petroleum. I was going to say petroleum mining. It doesn't work like that. Drilling for natural gas, but particularly for petroleum to make gasoline. Because the natural gas and the petroleum fill aquifers the same way water does. And so they drill where they're likely to find trapped petroleum, or they don't look for gas, they get gas sometimes if the rocks have gotten too hot. But anyway, I just wanted to point out that it's not just water that can fill up an aquifer. Okay, so here, just the last couple of things. Septic tanks. There's another example of what can pollute. So not everybody is on the sewer system. I lived in a house for 15 years that had a septic tank. Those can leak. How would I ever know unless it got so bad it got to the surface of the ground? I wouldn't. I don't think I would know. So that can pollute water. So here's a well pumping pure water, not for long, because it's going to start pumping septic disgustingness. Same idea here. So, and you can also draw, depending on like how much pumping you're doing in the wells, you can pull those pollutants toward you and actually make it worse. This is the cone of depression I was talking about. Here are 3 wells, well 1, 2, 3. Here's the water table between the gray and the tan rock, okay? This well at the house is pumping water, and they're pumping a bit too much because there's this little cone of depression there. This well's doing all right, but it's a deep well. This one's doing all right. It's met the water table. If this guy if they all start pumping a lot, and particularly if this guy pumps too heavily, and this could happen completely in the Salinas Valley where all those wineries are, they're doing this. And there are no laws regulating, there are hardly any laws regulating groundwater usage. So if you have the money to build a well, you can take as much water as you like. It's really quite crazy. It's like the Wild West as far as groundwater is concerned. Okay, so the point is you can actually have your wells run dry. And then, like I said, you'd have to drill deeper and deeper wells, and that gets more and more expensive. And so it can be too expensive. Okay, this is the same example, but here's the saltwater contamination. Here's the example of fresh groundwater here that is above salt water, which is denser and is heavier. So it's going to go seep into any aquifer below the fresh groundwater. Well, if you tap too much, if you tap through your water table and through the groundwater, you can actually pull in salt water, and then you've killed your well. Last thing, I promise. You can definitely use too much groundwater. In the San Joaquin Valley, so like I said, there are hardly any laws governing groundwater tapping. This is an example of this is a guy he looks like it's 1977. This is the surface of the ground surface. What am I trying to say? At 1977. In 1925, it was here. this much land had subsided, and here's an example of the subsidence, right? It's dropping down, literally dropping down, because the pore space is collapsing. You had grains that were supporting a lot of pore space in an aquifer. You take out the water and you can actually have those grains collapse and compact. And you've lost the pore space that would otherwise be your aquifer. And that's what's happened here. So they've tapped, and this is agricultural fields, right? Have tapped so much water that they've actually the land has subsided. Yeah, that's no good. Anyway, you can't recover. You might be able to recover a little bit of that pore space by pumping water back in, but you're never going to recover the full amount of pore space to achieve this same elevation for your ground level again. All right, that's it, you guys. I'm 3 minutes late. I apologize, but thank you. Thanks for bearing with me this semester. I hope you feel like you learned a lot, and I hope you feel ready to take the final. If you're interested in earth sciences, whether it's hydrology, looking at groundwater, surface water, rocks, or paleoclimate, oceanography, come talk to me, and I'll let you know what possibilities are for a major or a minor in earth sciences. And earth sciences minor goes great with lots of other degrees. And do you have any questions before the final exam?
Do we meet at all next week?
Nope. This is it. It's just final exam. So the final exam will open online like the other exams have. We have a scheduled final exam period, but we're not going to use it. You have a week.
When does the exam close?
I have to look it up. Let's see. I put it right on the, okay, so right. So on iLearn, it says it opens Monday, December 14th, closes Friday just before midnight, December 18th. So
I see. I see.
All of finals week to take it.
Okay.
Okay. It's going to be similar style, similar length to the other exams. No more questions? Okay. Good luck, everybody. If you haven't taken all the online quizzes, it's really important that you do that and take them until you feel like you understand the questions and the answers, because you're going to see similar stuff on the final, just like you have in the past exams. I hope that to give you diagrams and other things to interpret like I have in the past as well.
Thank you.
Okay. Thanks. Good luck, everybody. Have a good winter break if I don't talk to you before
Thank you.
then.
Thank
Bye.
you.
Thank
Bye.
you.
Thank you, guys.
Thank you. See you next semester.
Okay. Yeah, I'll see you. All right. Hey, dude.